Hello, morning class. Let's begin today's lecture. So, first thing first. Amy, you emailed me about the exam time, right? So we can discuss about this after the class. Okay, we will spend a few minutes to talk about that. So for the last lecture, we discussed about the Flory-Hagen theory and regular solution theory, to be specific. So today we're going to first recap what we talked about in regular solution theory. Then we're going to talk about how to extend it into Flory-Hagen theory. The difference between these two are regular solution theory. It's just mostly talking about small molecular solvent-solvent mixture. There's no connectivity between different molecular. And all these calculations between delta S, the different entropy of mixing, and delta H, enthalpy of mixing, is concerning small molecular. And at the end of the last lecture, we covered both entropy and enthalpy. We did a quite in-depth calculation about how can we address each portion of it. And we reached the conclusion how to get delta G of mixing is equal to RT, gas constant T temperature, times N1 number of moleculars in first molecular. Log x1 is volume fraction. I'll get to you, Amy, just in a second. Plus N2 times log x2 plus N1 times x2 times chi. So this is number of first molecular volume fraction, or this is would be number fraction in this case. X2 equals to N2 divided by N1 plus N2 and times chi. Okay? You have a question, Amy?
Yeah, so you were saying this is regular solution theory, but chi was the Flory-Huggins parameter. So is this regular solution theory for small molecules still, or is this Flory-Huggins?
This is a regular solution theory.
Okay.
Yes, when we talk about Flory-Hagen theory, this equation will not be the same, okay? But you can have chi interaction between small molecular and small molecular. It's just the name of this parameter. Okay, so we can understand how this is being done. And there's several different variants how we write about Flory-Hagen parameter, as well as this delta G. And you can see here is two variants. If you can take a look, tell me what the difference of these two variants are. Instead of we use N1, we replace with x1. Instead of N2, we replace x2. And how does that make sense?
Because you're changing your constant from R to K.
Because we changed, yes, but it still doesn't explain everything. Joseph is saying we just changed R to K. Yes, that's one difference. And the major difference between these two is I marked. This would mean delta G mixing persistent. So what do we mean by persistent? Persistent is every single entity. We add them together. Okay, that's just a bottle with two more molecular. Since when we discuss about Flory-Hagen series or regular theory, we don't need to know exact number of delta G. We're mostly concerned about if the delta G will be positive or negative. A lot of time people also use a second way to discuss about that is using the total delta G divided by how much lattice units in that. How much lattice units is basically sum of both molecular, right? So you can see the bottom is per lattice site. Okay, how many lattice total sites in the system? There will be N1 plus N2 times 1 mole, right? Remember that? So if you divide this by Avogadro constant and divide N1 plus N2, so R will become K. N1 divided by N1 plus N2 will become X1. N2 will become X2. And this N1 become X1. The rest just stays. And this is something just more simpler to memorize because now it's perfect almost perfect symmetric. KT, Boltzmann constant temperature, x1 log x1, x2 log x2 plus x1, x2 chi. Right? Okay. So that's another way you can write it. It won't change the conclusion. So this absolute value will change. It will change by quite a bit. But if it's become a positive number in delta G, it won't change sign to be negative.
Could you repeat how to get how we move to the per lattice side equation?
Sure.
What was N1 equal to again? Or how-
So yeah, good question, Chris. N1 is number of moles per molecular one. Okay, so that, for example, if we have N1 could be equal to 1 mole of, let's use a toluene mixed with hexane. I'll give you some specific number, then it helps you to understand. Okay. So in this case, if we use the top equation, this will be RT times 1 times, this will be 0.5 times N2, this will be 0.5 again, right? So how about now X1? X1 defined as volume fraction. So that defined as N1 plus, divided by N1 plus N2. So this is just total mole. So in this case, this will be 0.5 or 50%.
Okay.
Right? But the question is how number of side or lattice is during the mixing. This we need to convert to number. 1 mole is 6 10 to the power of 23. Number of molecular. So if we convert to the bottom one, we can use let's call it delta G mix. Here is persistent divided by number of lattice side persistent. So in this case, number of lattice will be 1 times 10 to the power 23 plus another 1 times 10 to the power 23. Okay, makes sense? Joseph?
Is
Yeah.
X1 and X2 the volume fraction or like the mole fraction?
This would be mole fraction, but they're actually interchangeable if they assume the same volume.
Okay.
Okay, because each molecule we had assumption before that they're just going to fill one lattice.
Right. Okay. Yeah, you're right.
So, mole, in this scenario, it will be mixing. But we will talk about today when we mix 1 mole of polystyrene and 1 mole of toluene. Then it's not the same because one polystyrene chain will occupy multiple lattice. Okay? So that's what the goal of today. We're going to talk about that and go to the Flory-Huggins theory. So I'll give you guys a quick example. Jen, yes?
Yeah, the number of lattice is 1 times 10 23rd.
10 to the power 23. That's just 1 mole.
I mean, why not 6 times 10?
Oh, I missed the 6. Sorry. 1 mole is, I think I write this wrong. 1 mole is 10 to the power of 23.
You were right. 1 mole is 6.
What?
Yeah.
Okay. My apology.
Yeah, so I think, yeah.
Okay. Sometimes I make stupid mistake. Today is the day. Are we all good now? Let's move on. So, give you guys one example. So, example is if we mix 1 toluene versus 1 mole of cyclohexane. Assuming we give you a chi parameter, this will be 0.24. Will those two solutions mix? And the criteria if they will mix is if delta G will be bigger than 0, it will not mix. That means after you blend them together versus what they have before, you increase free energy. This will not be allowed by the system. If your free energy drops, that means you take free energy out of system, that is preferred. So we can just apply the delta Gm for the system, and we can calculate. Okay, so this is the exact equation I copied. So N1 log x1 plus N2 log x2. This will be the entropy contribution, and this would be the enthalpy. So what is N1 and X1, Amy, in this case?
N1 is 1 mole.
Yes.
And X1 is 0.5.
0.5. Yes. Okay, great. So that applies to sane, right? N2, everybody got that? Okay, N2 would be 1. This will be log n. Then we can add the enthalpy term, 1 times 0.5 times chi. So I kind of applied here for you guys and use my calculator to calculate, because log n 0.5 I cannot memorize it, but you got the idea. Log n 0.5 will be minus 0.693. That will be the entropy of mixing for part of molecular 1 toluene. This will be entropy for the hexane. So if we add together, this will be the entropy gain for the system. What about enthalpy? We talked about chi is 0.24. It's a chi actually you can measure. So 1 times 0.5 times this will be the enthalpy. So this will be the enthalpy contribution, 0.12. So if we add everything together, you can see we have a net delta G of minus 1.26. That means we will have a system that favors mixing. Make sense? So this is how you can address if you have small molecular, if they want to see if they're going to mix, what the case will be, okay? So in this case, entropy is much bigger than enthalpy. What if we have a chi of 24 instead of 0.24? That's really high chi. Very, very high. Okay? If you have chi of 24, 1 times 0.5 times 24, this will become 12. Then the minus 0.693 doubles, and plus a 12 will be a positive value. So this will not favor mixing if chi is very big. And you can even calculate when does the chi will make it, if it's going to be the boundary of mixing or not mixing. You can use the same equation to treat the system. Okay? So this would be a system that I hope everybody give you some idea how we can calculate energy of mixing for using the regular solution theory if you know the chi value. And you can see if it's mixed or not. Really depend on chi. Because this value will always be negative, and this value determines your system will mix or not. Okay, let's deal with something more interesting. Now we move into the Flory-Hagen theory. Flory-Hagen theory is based upon regular solution theory. So if you already know the regular solution theory, this will be pretty straightforward, okay? So what is this? In this case, this theory is for describing a polymer in solvent that is similar to the regular solution, but of course we need to make some changes because we can't squeeze a polymer into one lattice. So this is the low molecular weight systems. You can think about just a solution theory. You can also think about this can be an example of mixing two low molecular weight polymer oligomers if we increase the lattice size to fit each molecule, okay? So this would be the polymer solution, and in this scenario, the white dots represent the solvents. The black dots represent the polymer. And in this case, we cannot say the polymer will occupy one lattice because it's pretty big compared to molecular for a single polymer chain. So we can define this polymer occupy more lattice. In this case, I think it's occupied 13 lattice. And how many lattice it will occupy depends on how big your molecule. And you might ask, when does the polymer occupy one lattice? And how does it compare? So in this case, we need to define a unit volume, or lattice volume. This lattice volume will determine the volume of total polymer chain, how much it needs to occupy. So for now, all you need to know is the polymer will occupy multiple lattice. It depends on how bulky the polymer, it will occupy more and more lattice, the bigger the polymer is. Make sense? Okay? So the key part in this scenario will be we need to understand how much volume will be occupied by each component. In this case, we already talked about, okay? So any questions so far? So in this case, we mixed 3 polymer chain with tons of solutions. So this would be the example of a dilute polymer solutions. You can think about dissolving like 1 grams of polystyrene in 1 liter of toluene. This would be the scenario, okay? So, as I said, they are very similar. So we just need to understand the solution mixing the thermodynamics under the context of entropy and enthalpy change. So how does the entropy changes for the system? Can we still use the equation we have? So this was the entropy, right? And this would be the enthalpy. This is a chi, and this would be the enthalpy term. So how much we need to modify it? Because they are very related, so we just need to think about how much we need to modify them. I'll let everybody think 30 seconds, and we can discuss about how each part. I can tell you definitely need to modify it. Otherwise, we just call one theory. We don't need to distinguish one from the other. And the question is how we need to consider the difference. So luckily that we only need to modify 1 major component out of 2. Zoe?
Would it be number of monomer units instead of moles? So N instead of, like capital N instead of N?
N, you mean this?
Yes.
It will be related. It will be related to N. Okay? Very good. We need to consider how long the polymer is, and in this case, we're going to use the degree of permutation N, taking into consideration how long the chains come into play. Right? Because N will impact how many lattice it occupies and how much entropy we can calculate. So this definitely need a modification. So modified to be enthalpy, we can take a look together. Okay? So let's take a look how we should discuss this problem. We're going to define something slightly different. So this is related to what Joseph has talked about. So for mixture of any type, we can define the volume fraction. In the case when each molecule has the same volume fraction, we can just write as this. But for polymers, we need to consider different volume. So you can think about phi 1 is one of the component would be volume of itself divided by total volume. And this will be the second component and vice versa. So now let's take a look at how much volumes that solvent takes and how much volume the polymer would take in the mixture. So how much volume of solvent is very easy. We assume each lattice occupy a volume of V0, So V0 defined as the volume of this tiny white dots. And since each solvent just occupy one, we can use how many moles of, how many number of solvent, this is not mole, this is number, times each unit's volume, we get total volume of solvents. So for example, if we have 1 moles of toluene, this will be 1 times 6 power 23 times V0. V0 just a constant term, okay? So the polymer volume it occupies, we need unit volume times the number. And since each polymer occupies more than lattice, so we need times this N, capital N. And this is for each molecular, it takes n number of lattice. And we will define N more precisely later. You can see it will be relevant to degree of polymerization. So in this case, we can define volume fraction of the solvents will be phi1. So the total volume will be V0M1 plus V0N1M2. So the phi1, the volume fraction of the solvents, V0 will cancel each other out from the top and bottom. So you would only left with M1 divided by M1 plus M2. And for the solvents, for the polymer volume fraction, it will be defined by the later equation. Questions? I mean, the only difference with regular lattice series is that now we would have a polymer occupies more than one lattice, and that's where we need to take into consider of that. And it has huge impact on entropy of mixing, which we will see just in a moment. That's the goal of today, okay? So the polymer is bigger and fatter, it will occupy more space. Yes?
Is there some
Daniel.
size differential at which this assumption doesn't really make sense anymore? Like nylon 612 in water or something, right? Like one monomer of 612 is way bigger than one monomer of water. Yeah. That's totally, what Daniel's saying is we need to consider what would be this case. So in that scenario, your nylon degree of polymerization N will not be equal to the lattice it's occupied. So everything is normalized to lattice unit size. In here is V0, okay? So V0 is the key, which you can see that just assume polymer occupies more volume for now. This more volume of occupying will depend on N, number of lattice. All right, so we're getting close. So we will have the similar problems, but now first part is considered the entropy. We talked about entropy of mixing for regular solution series, but when we fill the systems with polymer, it will be far more difficult because you can't put in random spots. Particularly for polymer one, because when you discuss about entropy, the first unit can be filled in any sites because it's empty chessboard. You can think about that. You can put it in there. But the second units for polymer must be located next to it, right? So that's what defines how many possibility. And what this Z means, just nearest neighbor. In this case, Z would be equal to 4 if we have this particular planar 2D lattice. So that means when you put the first one, let's assume this would be the first one. You can pick anywhere, but when you fill this one, the second polymer unit N has to be one of those 4 because it has to be connected. Otherwise, it's not a polymer. Just so on and so forth. And the next one will have Z minus 1 possibility. So you can see every single unit will be restricted in this case when we think about the polymer filling the lattice. It's not as going to be the case when we fill the solvents. We can pick one the possibility of first molecule will be the same, M1 plus N plus times M2. The second one will be the total sites minus 1. Right? Instead of now, we changed the possibility of second one tremendously by almost a factor of a mole. Think about if you're mixing 1 mole of toluene, 1 mole of hexane. The first toluene can be any lattice 610 to the power of 23. The second one 610 to the power of 23 minus 1, so, which is equally infinitely big. But if you put a polymer, the first one feels the same possibility, but the second one is just 4. 4 is much, much smaller than 610 to the power of 3. So in this case, the mixing of a small molecule, we only need to consider in configuration of entropy. Since the pure state, everybody still remember, when we don't mix them, the number of possible states, the omega equal to 1. So the S of pure state, before we mix them, S equals to 0. So when we discussed about that, it's much easy. But for the polymer, before we mix them, the conformation is not exactly 0. Okay? So we need to make one simple assumption that is related to the polymer phase before we mix them. Your conformation degree of freedom in the pure state and mixed states will be equal. So when we mix them, the change in the entropy is only associated with translational states. So the number of different possible states we can put in the different number of mass. So this is just a one simple assumption for the polymer state because you have configuration. What configuration is, we talk about a polymer chain can be configured this way and that way will be different. But in this case, if we only consider center of mass, how we feel the lattice, we can simplify greatly how we use Flory-Hagen theory. That's all you guys need to know. So let's apply a little bit. So this will be in the homogeneous states. You have.
Sorry, can you repeat the last assumption?
Yes. The assumption is, so let's go, do you understand the first part when we talk about pure solvents? But when polymer is before mixing, the entropy is not exactly 0.
Yeah.
So because you have different ways of chain can move and sometimes stretch, sometimes not so stretched. So the S for the initial states before we mix them is not exactly 0. So we need to give it a S value and state that this coming from conformation of freedom in the pure and mixed states will be equal. So we don't need to configure the configuration of entropy. We only need to consider the possible way of we generate independent different states in the mixed states.
So we're assuming like it's a pretty good solvent?
It's not related to the solvent. It's just entropy of the polymer. Let's try to listen to the next slide. It probably will help you clarify it. Let's give it a try, Amy?
Sure.
Because the next slide is very related. So this helps everybody to understand what would be the entropy of mixing when we consider its mixed states. So the conclusion, let's first talk about that. Delta X mix will be equals to Boltzmann constant, M1 log in phi 1, and M2 log in phi 2. This is number of molecular. So this equation is exactly the same except compared to the last regular solution theory. Now we're using a log in phi 1 and log in phi 2 instead of volume fraction, instead of x1 and x2. Okay? And everybody clear about what difference between x1 and x2? Everybody clear? So let's clarify here. X1 for the solution theory, x1 is equal to this. Phi is the volume fraction. So this is a mole fraction or molecular
number fraction. Phi 1 equals, again, N1. This would be the volume fraction, but since each N2 occupies more volume, we need to modify this. Okay? So this would be what we need to reach. So how do we get there? So use the assumption we have. We can say that in a different homogeneous different states, the number of different states for the molecular 1, 2 will be total number. This will be the arbitrary number of the system. So now when we mix them, now the lattice occupied by the first molecular will be less. So this will be the total number of states before we mix them. Then this will be times phi 1. So after mixing, your configuration entropy will be discounted. What's the volume fraction of this? This will be what is the phi 1. So for the mixing of the species, what we have, we need a KT ln phi 1. So this will be after mixing minus what we had before mixing for polymer. So we need to play a trick in the ln operation. So when you have ln phi 1, 2 minus ln 1, we can write as ln phi 1, 2, omega 1, 2 divided by omega 1. And this will be directly related to the phi 1 because this number of total states can cancel each other out. So you would end it up with K ln phi 1. This will be the entropy of the mixing of the first molecular. In this case, that would be the solvents, and we can apply the same to the polymer states. That will be K ln phi 2. That's how we get the entropy of the system. And you might ask, it looks exactly the same as what we have regular solutions here, but they are not. Remember, we have phi 1 and phi 2 instead of x1 and x2. And I'll explain why they're not. Because this slide explains more clearly what is the difference between phi 1 and phi 2. So I highlight the difference, the entropy of mixing. For Flory-Huggins units, we have those two parameters, phi 1, phi 2. And for regular solution theory, we have x1 and x2. So if we normalize by lattice sites, everybody understand how many lattice sites we have? We have total of lattice site equal to M1 plus N times M2 because each molecular of the polymer occupies more volume. So if we normalize per lattice sites, this is what we will have. Delta S mix equal to minus chi phi 1 ln phi 1 plus phi 2 divided by n ln phi 2. So let me explain physical meanings to you guys. You might a bit lost because we go through all these phi's x and phi x. So in essence, if we think about mixing 1 mole of toluene versus 1 mole of polystyrene. Let's use this example. The entropy contribution from the solvent is more or less the same. Okay, phi 1 is equal to 0.5, so 0.5 times ln 0.5. It's almost exactly. But now when we think about the entropy contribution from the polymer, it's much lower. That's because when we before and after mix, there's not much change in entropy in polymer. And why? Because this is still going to be 0.5, but divide by n. Imagine your polymer has dP not too high and each polymer occupies 100 lattice. You know, that's not too big a molecular. This would need to be divided by 100. So your entropy of mixing from your polymer will be much smaller than what coming from your solvents. Okay?
So let me repeat the important conclusion twice. When you have a degree of polymerization, usually the N is large. That means entropy contribution from your polymer is negligible. So the polymer don't contribute to the process of mixing in terms of entropy. Imagine this N is 1,000. This will, any large number divided by 1,000 will be very small, almost closer to 0. Okay? So the connection of those monomers into the chain drastically reduces the number of possible states for the system. This is because we are all connected for the polymer. That's why you don't change much entropy before and after. So while entropy is still promoting the mixing for the polymer, but it's not going to be as big as small molecular and small molecular mixing. Okay, so because this is coming from solvent, this is coming from polymer. Polymer don't contribute much entropy anymore. That's the difference. Everybody clear? And we will have an example at the end to show you guys how to calculate in a case when we mix the solvents with the polymer. Yeah, Amy?
Can you go back to the previous slide?
Yes.
So I don't understand this L with the slash through it.
L is just assume a number of different states for the system it would have, because the entropy for the polymer will not be the 0 before we mix it. We just give it a constant L.
Okay.
So you can imagine it will be a number of different states for the polymer could have. It can be 1,000. So before we mix it, it's not 0. Not like the solvents. It doesn't matter where it goes. So delta, the S before we mix it is always going to be one possible states. But when we arrange the polymer, you have different ways you can arrange them. I'll give you an example. So let's use 3 by 3 grids. If we now put the three polymers there, each occupies 3 lattice, you can see I can put them this way. That would be one way of feel it, right? I could also put in this way. That will be same 3 molecular in a beaker. So the number of different states is not equal to 1 for polymer before we mix them. And since it doesn't matter that much, we would just say this is the number of states for phi before we mix the polymer. Okay? And after we mix the number of states for the polymer will be related to the volume fraction of polymer times this number. That's all we're saying here. All right, let's move on because we have, I want to finish this chapter in the next 20 minutes. So the other part we need to talk about the enthalpy. We talked about entropy. Entropy will be smaller, but how about enthalpy? So I again listed 2 parameters. Turns out enthalpy is not much big differences. It's still, again, the interaction between the solvents and the polymer. So you can see the regular solution theory regards as number of solvents molecular times x2, volume fraction times chi times kt. And in the Flory-Huggins theory, it's more or less translated to here. So we just need to know in terms of enthalpy, number of solvents molecular, volume fraction of the polymer, chi times kt. So you can think about that's more or less the same. And we did one proximity is that we basically takes away, in this case, each monomer has 2 neighbors. You're going to occupy interaction you always have with 2 neighbors, then the other 2 can have interaction z minus 2. But this won't change our conclusion. If we combine the enthalpy and entropy, this would come to the Flory-Huggins theory. And here is a nice picture of Paul Flory, who got the Nobel Prize in '74, almost 50 years ago. So that's what he deduced from his simple pen and paper. Delta G mixing for the polymer will be equals to KT M1 number, so how many numbers of molecular for the solvents, volume fraction of the solvents, number of polymer chain you have, volume fraction of polymer chain, and again, number of solvents, volume fraction of polymer times K. This is one way you can write. Sarah, you have a question?
Are we missing a negative sign in front of the K or R, or does that not translate to the Flory-Huggins theory?
No, we are not missing any.
Okay,
So this should be the right one.
okay.
Then we can also get the delta G per lattice. All we need to do is normalize by total number of lattice, which will be M1 plus M2 times M. So if we do a normalization, we would reach this equation, which is phi 1 log in phi 1, phi 2 log in phi 2, plus phi 1 phi 2 chi. That's per lattice because we basically divide by total number of lattice. And M1 divided by total number of lattice will translate to phi 1. But N2 divided by number of lattice will not translate to phi 2 because M2 plus phi 2 would be N2 times N divided by total number of lattice. So just pay a little bit of attention there. There is the factor of N comes into play, and plus phi 1 phi 2 times chi. And again, same argument as a regular theory. So this part contributing to the entropy of this mixing. And this is the enthalpy of mixing. And if you remember what we write in the number of different lattice for regular solution theory, this would be x1 times log x1, x2 times log x2 plus x1, x2 chi. If they're equal volume, you can basically translate x1 to phi 1. But if they are not equal volume, then you need to normalize by n. So what this says, we will learn in the one example. I'll give you an example, then you guys will learn this much easier. So this would be example. What is the free energy when we mix polystyrene with a molecular weight about 10,000 grams per mole, dissolved in cyclohexane at this temperature and yield 10% solution by volume? So we tell you all these parameters, except we didn't tell you chi, that we will be able to find later. So this gives you the chi. So imagine we just tell you chi equals to 0.5. So we also give you the volume fraction, phi 1. Phi 2 is 0.1, 10% solution. Remember, phi 2 is where the polymer is. Phi 1 is where the solvent is. Right? You have 10% volume of polystyrene, 90% volume of, in this case, this would be cyclohexane. If we get the molecular, if we give you the molecular weight, we can also identify the different lattice constant. Okay? So shall we jump in, everybody? That will be the only goal. So in the first example, the first task is we need to calculate number of solvent molecular and polymer molecular. So this, we are calculating M1 and N2. How do we do that? We're just going to use the density of each molecular, and we know the volume. We can normalize them. And this would be one way. You can use other ways to calculate it. So this, you can look it up, the density, or this would be the molecular weight of cyclohexane versus its density. You can get how much volume each mole of polymer would have. Does that make sense? So why do we need this number? Then we can assume we are mixing 0.9 cubic centimeter of, this would be the cyclohexane, and 0.1 cubic meter of polymer. We can use this to calculate how much moles we have. Because you use this number divided by unit volume per mole, we can get, it actually is equal to mixing 0.0083 mole of solvents together with, I jumped to one step here, I didn't give you number of mole, but you use the number of mole times Avogadro constant, 6 times power of 23. You can see this would be the N1 for the molecular, this would be the N1 for the polymer. I'll give you a second to digest. This would be one way you can do that. Okay. The other way you can do that is just, if I tell you the volume fraction, you can assume this will be 0.1 grams. Wait, let me get an eraser. You will reach the same conclusion if you use the other way to get how many moles of polymer versus solvent. The other way would be, you have the volume, it's 0.1 or 10% is polymer. So you can use the same, assume this is a 0.1 cubic centimeter. And so this would be the polymer. And you can also use the solvent. This would be 0.9 cubic centimeter. That is the same, assuming you have 10% volume. You can use this, convert to weight by times the density. So density is volume times density will give you mass. And if you divide by molecular weight, it will tell you how much mole of polymer. It will go through the exactly same process. Okay? So now we know number of moles for the number of molecular for each. We can use this particular equation to calculate delta G of mixing. So in this case, we first have, let me make sure. So this will be the Avogadro, this will be the T, Boltzmann constant. T is the temperature of mixing in the units of Kelvin, 300 something. You can omit that if you don't want, because this won't change the sign. But then you can times the volume the number of molecular N1 times log in the volume fraction of phi1, plus another number of mole of polymer times log in phi2. And add the chi parameter, number of molecular, volume fraction, chi. This will tell you if this would be mixed or not. Your total delta GM is, if you did every number correctly, equal to minus 1.24 joule. That would be the units of the mixing. So will it mix or not? Yeah, it definitely will mix, right? Because it's a very negative number. But if you go back on your computer or on your calculator, you can see this number is the entropy of mixing for the solvents. This number is entropy of mixing for the polymer. This is about 1,000 times bigger because these two numbers does differ that much. But if you see, this is 5 to the 10 to the power of 21. This is 10 to the power of 18. So the entropy of mixing in this case plays a quite big role. It's mostly coming from solvents. So the solvent entropy of mixing is actually larger than the chi. That's why it can promote the system into the mixed states. Okay? Questions so far? It's pretty much the same as the regular solution theory, except that when we calculate the entropy, we need to be careful and because the entropy of mixing for the second part of the molecule is usually very small compared to the solvent. And how small is usually defined by the difference in molecular weight. So remember, this would be the polystyrene, and if you normalize by unit molecular weight, you can get the difference. So, okay, 2 more. So I hope I kind of convinced that from the 2 calculations we did in the regular solution theory and polymer solution mixture, your entropy always favors mixing. No question about that. No matter what kind of mixing ratio, your entropy always wants system to be mixed. Even in the cases when you mix a solvent versus polymer, well, the polymer don't contribute a lot, but solvent says, let's do it. It's always contribute a lot of entropy, right? So now it's basically a tug of war between the entropy and enthalpy. Entropy always say, let's go mixing. Enthalpy, let's say, wait a second, let's think this through. And how do we define the magnitude of enthalpy is constant to this chi, Flory-Huggins parameter. And I kind of showed you that in the first example, when chi equal to 0.24, this will favor mixing, but when chi goes up, your system disfavors mixing. So what's this chi parameter? What is it, and how do we understand that better? So first is you can't look at chi parameter is table, and you can find a chi parameter in literature. And it's typically reported by a pair of systems. When we say a pair, it needs to be 2 systems, because chi is a pair interaction between one to the other. So you wouldn't be able to find a chi for polystyrene, but you will be able to find a chi between polystyrene and PMMA, for example, or polystyrene and a solvent. Okay, so it always need to be pair, 2 systems, solvent or polymer. Depends on a lot of different conditions. And chi parameter would also change with temperature, chemical structure. So pay attention to that. And since we talk about entropy always favors mixing, chi parameter is actually predicted 2 components it will be mixed or not. So we give you 3 examples. Chi is a positive number. This is the most commonly seen. For most of pair, you would find a lot of time chi will be bigger than 0. Chi could be negative, but it's a rare case. And chi possibly can be exactly 0. That means there's no heat exchange before and mixing. So the molecular, remember, chi equals to the self-pair interaction versus the hetero-pair interaction. When chi is negative, let's look at the both bottom one. Your thermodynamics always say we're going to mix it because your entropy favors mixing and enthalpy also favors mixing. So there's no way you can make delta G positive because everything is negative. Sounds very sad to say that. Everything is negative. When chi equals to 0, your enthalpy term will be exactly 0. Because enthalpy equals to x1, x2 times chi. If chi is 0, that means that whole term is exactly 0. So this is what we call ideal mixing. There's no energy change of the system in terms of enthalpic perspective. But remember, we still have entropy. Entropy is negative. So even enthalpy is 0, 0 plus the negative term will be favor mixing as well. The only case you could have mix or non-mix is in the case as chi is positive. But now this depends on the magnitude of your chi versus the entropy of the system, mixing of the system. So if the entropy of the system is bigger than the enthalpy term, you will favor mixing. But if this is really positive, your entropy will not overpower that. So in this case, you will not mix. Amy, yes.
The statement at the, like the second to the bottom statement, that doesn't seem to make sense to me, because you would think if it dissolves, like if like dissolves like, then X would be negative.
Yes, but what you stated is true, but things, I told you that this example is very rare. So most of cases, it's always going to be the chi equals the positive number for most of pair mixing system. So when the scenario, when Amy mentioned when like dissolves the like, in this case, you will have a small chi. That means your chi is still positive, but it will need to be fairly small. So in this case, it didn't hinder the system from mixing. Okay, does that make sense? You are right about it need to be, enthalpy need to be favor mixing. But in that case, you typically don't find enthalpy to be negative. So as long as your enthalpy is a small number, that will be fine. Questions? Chris, please.
How would you find the chi parameter?
Did you read my mind? 'Cause I listed the one to you.
I wish I could actually.
Let me try to make it bigger, because that is a bit harder to see. It will list different values of chi's. So you can look up upon my handbook. So this will be example of polybutadiene, this polymer in different solvents. This will be the temperature, and this would be the chi parameter. You can see it typically changes. And for example, this will be a small chi value. Let's take a look. So chloroform dissolved butadiene should be very well. If I compare these two pairs, the chi is very little. So let's see, this is very high chi. Chi equals to 2 is typically considered to be large. Let's take a look. Let's use this one, 2.78. Butanol, this will be echo. You're not going to dissolve butadiene. This will be several examples. Let's see, is there anything we are more familiar with? Isoprene, polyamides, mesacrates. Yeah, these are all the. There's more example, you can look it up. But this gives you some idea how to look up chi parameters. Okay? So if we ever have an exam, I'll give you the chi parameter, so you don't need to worry about look up chi stuff. And even in the homework, the chi parameter should be given to you guys. Oh, there's one more slide I want to go through before we talk about. But chi parameter is something in the theory people also know it's oversimplify many things. So every theory has its limitation. So what's the limitation for Flory-Huggins theory? Or using Flory-Huggins equation to calculate if system will mix or not. 99.9% chance you will find it predicted the mixing successfully, but there's also chances will not predict the mixing successfully. So approximation we made about counting configuration is a reasonable good approximation, not perfect. It turns out to be it's not a too big a factor. So what we use to counting the entropy is fine. The volumetric effect is not perfectly worked out, because when you mix in solvents, when you mix other systems, we not always going to have the same number of lattice we're going to occupy. Sometimes there's volume shrinks when you mix solvents. I cannot name one on the top of my head, but if you mix 100 milliliter ethanol versus 100 milliliter water, it's not going to be exactly 100. Okay? So, and chi has a dependence on temperature in many cases. Because temperature also play a turn. That's why in many cases you will see chi is written as a function of temperature. So chi as a function of temperature is approximately equal to A is a constant, B is constant, and B divided by T. So what does this mean? That means when you change the temperature, chi could increase or decrease. So you cannot claim a chi for PS and cyclohexane. You have to give one more condition, is cyclohexane polystyrene at a given temperature. Because if you don't tell the temperature, it doesn't make sense. So this gives you example. This will be listed some of the polymers, Flory-Huggins parameter. And you can see some of them has a negative B and some of them has positive B. That will have influence. That means when you increase, decrease temperature, your chi will change. And sometimes change quite a lot. So that's why when you're heating or cooling, some system may not be mixing. It can be made mixed because you're changing the chi. Okay? Because the entropy don't change, but your chi is being actively controlled. Yeah, Sarah?
So in the example that we just worked, we had polystyrene at 34.5 degrees Celsius.
Right.
And there was a hint that said at that given specific temperature that chi parameter was half or 0.5.
Yes, yes.
Making it, I guess, theta condition. So how would we be able to identify when we're given a specific temperature, if that specific temperature is going to be like an ideal system?
Right.
Or?
Good question. So that's a bit beyond where we're going to go on the test because we haven't talked about, there's going to be another lecture about chi, and you will learn that in the osmotic pressure in the next 2-3 lectures, we're going to tell you why chi equals to 0.5 will happen to be the theta condition. We haven't taught that part, that's why I just want to give you the chi equals to 0.5 argument, but just to hold the question, we will go through that again.
Okay.
Later you will learn why chi equals to 0.5 will be the perfect theta condition. For now, that's everything I want to conclude, and I want everybody has next lecture we're going to talk about osmotic pressure. And before we go, I want to have one last question, let everybody think about this. So this is a case when we discuss about we mix a solvent versus a polymer. So what's going to happen when we try to blend two polymers, polystyrene and polyethylene? Can we use a modified Flory-Huggins theory to explain? The answer is yes. You absolutely can. And I'll give you guys a hint. You need to think about connectivity contribution to the entropy. The enthalpy term will be fine, but the entropy term need to modify it one more time to consider the volume of the first molecular we have blend versus the second polymer, right? So think a little bit, and we will discuss that in the beginning of next class. And if you think that through, it will give you a lot of aha moment that will explain why polymers just don't want mix with another polymer. You rarely find the case that polymer will be, let's mix, make a polymer alloy. You don't see that a lot. There's only a few occasion cases. All right, with that, let's wrap up. Thanks, everybody.